about 6 words we use to describe images. And the first set, we always use 3 of those 6 words when we're describing images. The first type of word we use is whether or not the image forms where the light is, or where the image forms where light is not. So what do we call it when an image forms where the light is? Real. It's a real image. And what do we call it when light forms, or when image forms where the light is not? Virtual. Okay. So if your brain basically takes in the information and says the image must be back there, it's virtual. Like behind a convex mirror or behind a flat mirror, we have a virtual image. And then we talk about how big the image is. Something can be either reduced or magnified. And then we determine its orientation. If it's flipped, what do we call it?
Inverted.
Inverted. Okay. If it's flipped over where the top ray becomes the bottom ray, we say it's inverted. If the top ray stays the top ray, we say it is what? Upright. Exactly. So an image will either be real or virtual, reduced or magnified, and then upright or inverted. That's what we left off with yesterday. Any questions so far before we do something new? Okay, do some really cool stuff. Mirror equation. Now, I'm going to give you the equations, and then we're going to talk about them, and then I'll show you what the variables represent. There's a mirror equation, which looks a lot like the lens equation we're going to be using later on. This is a mirror equation. 1 over f equals 1 over do plus 1 over di. Duty. 1 over f equals 1 over do plus 1 over di. What are these variables? F is called the focal length or the focal distance. It's the distance between the mirror and its focal point. I'll describe that in a second. Do is the distance from the mirror to the object on the principal axis, and di is the distance from the mirror to the image on the principal axis. So once you're done scribbling those formulas down, I will draw an example of this. It's okay. This formula relates the focal distance of a convex or a concave mirror to its radius of curvature. And it's kind of goofy. Now, when you're doing exercises, you may be given the radius of curvature of a mirror, or you may be given its focal length, because one can give you the other. So take a look at this. 1 over f equals 2 over r. I don't know why they just didn't make it a simpler formula, but maybe they just like the reciprocals. But if the focal distance is 2, what is the radius of curvature? 4. Okay? So take a look at this. I'm going to draw a diagram of a concave mirror. Concave mirror. There's my radius of curvature. That's where my shoulder was. That's the radius of curvature. That is the point at which every point to the mirror is the same. That's an R, that's an R, that's an R. Every point to this mirror is the same. This is a concave mirror. So if that's the radius of curvature, would you expect the focal distance to be on the left or the right? This is the mirror. Right here. And this is the principal axis. Okay, that's the principal axis. That's the radius of curvature. Using the formula, if the radius of curvature was that far from the mirror, where would you expect the focal distance to be? Halfway between, on the right. Okay, right there. Okay. That would be the focal distance, or the focal point, or the focal length of that mirror. And what's really great about this, especially if you like geometry, that means any ray that comes in parallel, strikes the mirror, will end up at the focal point. Every ray that comes in parallel to this mirror focal point. Now, hopefully this makes sense because the law of reflection still applies. Remember the law of reflection from yesterday? What goes in comes out at the same angle. Angle of incidence and angle of reflection are the same. Okay. So hopefully that makes sense. I mean, you have a huge angle up here, a very small angle here, but either way, regardless of where you are, understanding that the barrier is going to be always tangent to the curve, then the angle will always reflect back to the focal distance. This is kind of handy. Where do you use something like this? Where do they use this phenomenon? Writing glasses? Okay, that was a good guess, but it's wrong. But headlights, flashlights. You put a light there, the light basically gets projected in one direction. We don't want your, it wouldn't be useful for your headlights to basically project in every direction. If you put like a big old, just a giant light bulb in front of your car, it's going to project light in every direction. That's not helpful. You want to project light forward. So that's what you do. You put the light right there, and you put a mirror behind it. And the mirror produces the light forward. Okay, so this would be the focal distance, this F here. This would be the radius of curvature. And in this class, when we're talking about things called spin mirrors, then the principal axis, on the principal axis, the focal distance will be half the radius of curvature. Does that idea make sense? So you'll either be given, when it comes to a mirror, you'll either be given the radius of curvature or the focal distance. Now what are these? These are distances. I'll give you the diagram that we'll talk about the magnification. There we go. This is the distances. So here we have an object. The object projects light, strikes the mirror, the light then converges to create the image. The distance from the device to the object is DO. The distance from the device to the image is DI. The height of the object and the height of the image are just sizes. And magnification can be found two ways. It can be found as the ratio of the height of the image to the height of the object, or it can be found as the negative ratio of the distance of the image to the distance of the object. And I'll explain why that's kind of weird here in a second. DI and DO. Objects are always real. Objects are always real. DO will always be a positive number. Things that are real will be positive. Things that are virtual will be negative. So, if your object, which is a real object, gives you a positive DO, sometimes your image and your focal length will be negative. When that happens, your F and your DI have to be negative. Just to give you an example, I'm going to butcher the physics, but I'm just going to throw a number out here. If you had an object right there, this would be DO, from this point to the mirror. So far, so good? If it created an image that was over here, it has to be way over there, let me get smaller. So if you're getting an image that was like this would be DI, that distance to that point there. So far, so good? Sometimes it happens where this image is virtual. If this image is virtual, it gets a negative DI. And to cancel it out, a negative DI from a virtual image, well, this will get canceled out, and you'll have a negative of a negative, and you'll have a positive number. Okay. When we do diagramming, and actually do real-life examples of magnification and creating images, then this will actually make sense why you need a negative right there. You'd be like, oh, it has to be a negative DI because my DI was originally negative, I need to make it unnegative by using a negative of a negative. But that's what that is. For distance from the object to the mirror is the DO, from the mirror to the image is DI. The ratio of the two will give you the magnification, and the ratio of the heights will also give you magnification. Cannot wait till we do ray diagramming, which is going to happen Thursday. Tomorrow we have a really neat lab with lasers and prisms and stuff. Okay. Questions about this? Yeah.
Why is it on the other equation
because this equation is universal. You just have to remember that if you get a virtual DI, you need to put in a negative number here. It stays negative. Its negative will basically be important mathematically, geometrically. So if this distance was 20 centimeters, you would put 20 for DO. And focal distance, let's say this was 18, you'd put in 18. And then this distance was, let's say 13, you would put in negative 13 before you did your math, or you solve for one. One of those three things would be an unknown. So you basically measure that distance. Since it's virtual, it needs to be negative. DO will always be positive. F can be positive or negative, depending on the situation. And we'll get to that when we do lots and lots of diagrams. And we're going to do a lot of diagrams. Other questions? Okay. Take a little bit of a tangent and talk about wave movement phenomenon. 3 types of wave changes. Reflection, changes the angle. Refraction occurs because of a speed change. When a wave travels into a new medium, its speed may change, and that creates refraction. Slickest examples of this is when you open your car door on a hot day and you see those heat waves come out of your car. You know what I'm talking about? You open the door and there's all this hot air that comes out and you're like, ooh, look at the hot air. Well, you can't see air. The molecules are simply too small. But what you can see is hot air is less dense than cool air. So the hot air has a lower index of refraction than the cool air. In other words, the hot air, light travels faster through the hot air than it does through the cool air. And you can see that changes in speed as the air kind of ripples a little bit. Or when you pour something thick into something, like when you're diluting something, and you can see the little like squiggles in the drink, because the thick stuff has a different speed than the thin stuff. Another way to think of index of refraction is this. Now this is a complete model, in that it's not exactly right, but it works for us. Light is a 3-dimensional phenomenon. Pretend you're driving along in your car. You have 4 wheels. As far as the road's concerned, you're a 2-dimensional phenomenon. And then your tires on your right side of your car blow out. What does your car do? Yeah, it's going to pull that way, right? Because all of a sudden your wheel's a lot smaller. So your car is going to pull. Well, the same thing happens when light goes at an angle into a new medium. It gets pulled. It gets pulled based on whether it's speeding up or slowing down. If it's slowing down, it gets pulled differently than when it's speeding up. I'm going to give you a bunch of examples about that. I'm probably not doing it a very good explanation, but I'm trying my best. Okay. So diffraction occurs when light changes speed. And it changes speed when it goes from one medium to another medium. In a transverse wave, as density goes up, light slows down. Okay? So if it goes into a more dense medium, it slows down. So far so good? If you're getting bored, so we're moving on. The other thing it can do is diffraction. We're not going to spend a lot of time in diffraction because you pretty much don't really need it unless you're going to be taking the Physics AP2 test. So just going to mention what diffraction is, give you a general idea, and then move on. So this says diffraction can turn straight waves into curved waves, or vice versa.
What does that happen?
Diffraction? If you take something with sharp edges, and it might happen if you have enough light, probably not in the window, is take something with sharp edges and you hold it up to something bright, the sharp edges kind of get fuzzy, and because light bends around the sharp edges. The best analogy I can give you for diffraction is if you were carrying a bar or a box that was wider than your door, what would you have to do to get out of the door? Push harder. Just break the door down. No, if you had a box that was wider than your door, how can you get out of the door? Yeah, you turn, go through the door, and turn again. Okay, that's what light does when it goes around edges. There's an edge right here. It's like, oh, I have to turn to get around the edge, but it doesn't turn then turn. It just turns once and keeps going. Okay, so that's diffraction. Photographers have a big issue with diffraction. They always have to put the image they want or the object they want in frame, and everything else is going to be blurry. Partially for that reason. They get all sorts of crazy blurriness when you put a big light source behind something. Okay, this is what happens. Again, this is not in first year physics anymore. It's more in physics AP, but I'm going to mention it anyway because it's kind of cool. But wave energy will go and it'll strike a small boundary, and then the waves will bend around the corners of the boundary. And those straight waves will become curved waves. And then those curved waves will interfere. Remember interference? When you have wave energy that sums together, when they arithmetically add their amplitudes? Well, if the waves when they overlap, they can create a pattern on the screen where you have bright stripes representing the antinodes and dark stripes representing the nodes. Again, I don't want to spend a lot of time on it, but diffraction forms straight waves and curved waves. When the curved lines meet, antinodes are created at points of high energy. In the diagrams, the antinodes are shown as thick white lines, and the nodes are shown as thick dark lines. I don't want to spend a lot of time on it because diffraction simply isn't all that important at your level. Yeah?
Is that like when you were like look at the light through your shirt, you still see some of the light when it's not as bright?
Maybe, but I doubt it. It's probably just because the shirt's translucent. There's little gaps here and there. Okay, what is really cool is this. Now, we're going to go back to that cat and fish diagram. This is really, really important. We're going to talk about beams entering planes. Now, I mentioned before, light slows down when it enters more dense media. Because it slows down, its angles will also change. So consider our cat and fish diagram. The simplest diagram is right here. Now, a few bits of lingo. Theta I is the angle of incidence. Theta R is the angle of not reflection, but refraction. So light's going from cat to fish, angle of incidence, angle of refraction, still measured to the normal. Here's our boundary, here's our normal. Okay, where is my laser? There we go. Okay, I got some water up here. There's my water. And I don't know what the deal is with all these bubbles in the water, but there's just a lot of air. Ooh, there's just a lot of air in the bubbles these last few days, or in the water these last few days. So this is what I'm going to do. I'm going to put a mirror in the water, just for fun, because it's fun. And I'm going to shine a laser, just like in this case, from air to water. Big bright green laser. Boom. Okay. So see here? The water is the boundary plane. Where's the normal, if this is the boundary plane? Yeah, right here. Okay. So I'm going to shine it in there. You see it, and I can bounce it off the mirror too. Can you see the laser through the water? And it ends up there. Okay. Watch what happens when I change the angle of incidence. By the way, if this is the boundary plane right here, this is the angle of incidence. Remember, we always measure the angle of incidence to the normal. From the normal to the beam is the angle of incidence. So I'm going to change the angle of incidence, and something kind of interesting is going to happen. Can you see that? Yeah. Is my incident beam still lined up with my laser? Look at the water. Look where it is in the water. Oh, can I move it back here? Oh. Okay. So is my light beam still lined up with my laser? No. It bent. And this is my angle of incidence, and down there, that from the normal to the beam is the angle of refraction. Angle of incidence, angle of refraction. Which one's bigger? Really? The angle of incidence is bigger. If you actually look at the angle from here to the angle of refraction, this angle is a lot larger than this angle. Because when light energy strikes a different medium, it changes speed. And if you don't want to know the mechanics, if you don't care about the mechanics of optics, just remember this. Density up, angles down. If the density of the material is going up, the angles are going to go down, and vice versa. If the density is going down, the angle is going up. If you don't want to learn any of the mechanics, just remember density up, angle down. Which means when you're going into a more dense medium, the angle of refraction will be smaller than the angle of incidence. Angle of incidence, angle of refraction, density up, angle down. The angle is going to get smaller because the density increased. The opposite is also true. If our density is going down as water to air, density down, angle up. Because the light energy is speeding up from water to air, the angle is going to get larger. The angle of refraction will be larger than the angle of incidence.
So the light is actually going that direction. It's not how we're perceiving it.
Correct. Light is actually moving. Another way to think of it is, you guys don't mow lawns, but like imagine you're mowing a lawn and your lawnmower has 4 wheels, and then you hit a patch of mud on one of the wheels, your lawnmower is going to pull towards the mud. That's what the light's doing. It's getting to the edge, going boo, boo, hey, and over here, boo, 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 boo. Oh, this side, the front of the two-dimensional phenomenon, and then this side caught the water first and slowed down, so it turns towards the water. Does that make sense? So, just a light beam. Oh, the corner of me caught the water first, and it bends towards the water. Now, is this actually what's going on? Nope, but it's a really good model. You can figure out what's actually going on in about 5 years. Same thing here. I'm just a little water beam. Ooh, now this side gets to move fast. This side gets to move faster, and it's going to bend towards that side, and it makes the angle bigger. Because this side got to move faster, and it causes it to bend outward. Okay, if you want to know the mechanics, that's the mechanics. If you don't want to know, angle up, density down, density up, angle down. Okay, so there you go. The difference is due to something called the angle of index of refraction. So we assign a number, little n, to how fast something is going in a media versus space. Now remember, the speed of light in space is given the letter c, and it's 3.0 times 10 to the 8th meters per second. I will tell you right now, water's index of refraction is much larger than that of air. Water's index of refraction is 1.33. Air is 1.00. So, is light traveling faster in water or faster in air? Air. It's slowing down in water. Index of refraction is a ratio of c, the fastest light can go, and v, how fast it's going in a medium. What's the fraction going to look like? Is c going to be on top and v on the bottom? Or is v going to be on top and c is going to be on the bottom? Think about it for just like a minute. Index of refraction is a ratio of c to v or v to c. Water is 1.33, where light moves slower. Let's take a vote here in a second. So it's either going to be c over v or v over c. Who says it's going to be c over v? 1, 2, 3, 4, 5, 6, 7, 8. Who says it's going to be v over c? Good. C over v. In other words, nothing can travel faster than c, and when things slow down, you get a smaller v. Index of refraction is a number larger than 1. If your index of refraction is 2, that means you have speed that's half the speed of light. If your index of refraction was 3, you would have speed 1/3 the speed of light. No, Snell's law come up just yet. Okay, so that's the index of refraction. In air, air is pretty close to gas, pretty close to vacuum, so we just say 1. The other classes we're going to use, glass is usually 1.5 to 1.6. Water is 1.33. Everything else, Diamond is 2.4. The reason diamonds sparkle is because light travels relatively slow, Gesundheit, in water, in diamond. And we'll talk about why that is when we talk about internal reflection in a little bit. So you might think of index of refraction as our rating of speed of the material. If you have an index of refraction of 1, full speed. Index of refraction of 2, half speed. Index of refraction of 3, third speed. And so on. Never less than 1. As far as we know. Okay, and that allows us to do something really, really neat. If we realize that the energy itself can't be lost, then we can write something kind of cool. We can say the index of refraction, which determines the angle, has to be the index of refraction, which determines the angle. In other words, the index of refraction of incidence times the sine of the incident angle equals the index of refraction of the new material times the angle of refraction. Once you write that, I'm going to back up a slide so I can demonstrate what I'm talking about. Ni sine theta I equals Nr sine theta R. Some old textbooks still say Ni over Nr equals sine theta R over sine theta I. So if you ever see that in any textbook, you can use it on your own. Cross it out and write Ni sine theta I equals Nr sine theta R. This is the way it should be written. If you ever see them as fractions over equal a fraction. Okay, so back up. Okay, so what we're talking about is Ni, air, sine theta I, index of refraction, right, angle of incidence, equals Nr, water 1.33, times angle of refraction. IR. If the light's going this way, IR. Does this idea make sense? Then let's do one together. Okay. So, boundary. Put the light up here. We'll let the light go that way. What's this material on top? Air. Okay, make it easy on me. Air. Okay. Air has an index of refraction of 1.0. What's this material down here? Diamond. Okay. Diamond has an index of refraction of 2.4. So far, so good? So, light comes in. Bam! Hits there. This is the boundary. Where's the normal? Straight up and down. Okay. There's the normal. Can't believe I made the normal. The normal should be a dashed line. The light should be a solid line. There we go. Let's make this a solid line. Here comes the light. Okay. Where do I label the index or the angle of incidence? Angle of incidence. What is the angle of incidence? You just throw a number out. You have a question? Yeah. No, it's not 6. Just give me a number we can work with. Something in 45, 30, 45. Okay, 45 is nice. So 45 is easy. Okay, so we write our formula. Ni sine theta I equals Nr sine theta R. Ni is air, so it's 1.0. Sine of 45 degrees. Make sure your calculator is in degrees. And then R is going to be 2.4 times sine theta R. So Nr of our diamond is 2.4. Determine, if you can, what our angle is going to be. What will be our theta R?
lasers probably has some what's the reason for
The energy, the amount of energy they carry. So basically, when the light strikes the molecules, it has to turn around and reflect it. If it can't do it very efficiently, then that energy gets absorbed in the materials, eats it up. So it really doesn't matter, but the higher the frequency, the more energy per photon you have. So it's usually a blue laser. They usually do that with a blue laser because each photon has more energy. That's the realm of physics AP2. Generally, the higher the frequency, the more energy you're carrying per photon. So if you got an answer, give me a thumbs up. Don't blurt it out. I don't want to know what it is just yet. Okay. Take about 30 more seconds. For those who do have an answer, did you check your work? Since density went up, did the angle go down? Okay, what do you got for an angle? 17? Sounds good. 17 degrees. So, should I draw my line closer to the normal or further away? Closer to the normal. Probably something like that. So 17 degrees. And this is the angle of refraction. Okay? Since density went up, angle went down. Good job, Hughes. Okay. Nod your head if this makes sense. You're like, I think I get this stuff. Okay, cool. Any questions? Total internal reflection. I love this. Okay, watch this. I'm going to try my best. It worked pretty well last time without me spilling the water all over the place. But I gotta put this like right on the edge, right on the verge of falling over. I'm going to have a laser. I'm going to shine the laser in from the bottom. And what we care about is the light going from water to air. Okay. So see what's going on? Light's right up there on the ceiling. Okay. So light's right up there on the ceiling. The angle of incidence is now this angle right here. And the angle of refraction is this angle right up here. Watch what happens when I make the angle of incidence bigger. Again, as I put the angle lower, this angle here becomes bigger. Eventually, the laser disappears and ends up trapped in the water. Can you see it trapped in the water in there? It just reflects now. It's not able to leave because it's trapped. That is total internal reflection. This only happens when you're going from a larger dense medium to a less dense medium. Because if density goes down, angle will go up, right? But when angle gets to 90 degrees, it can't exceed 90 degrees. It can't cross the normal. So that's what happens with total internal reflection. If you have light going from a more dense medium to a less dense medium, like you're going from water to air, if density is going down, angle is going to go up. And eventually, so this is this angle, this is the angle of refraction, angle of incidence. Eventually, this angle of incidence will get so big that angle of refraction becomes 90. When that happens, the light gets trapped and we get total internal reflection. Light can't escape because you can't have the angle cross the normal, and it certainly can't cross the boundary plane. Again, it only happens when you go from a more dense medium to a less dense medium. And I have a really cool animation. I think you're going to like it. I love it. Okay, so here is index of refraction. I'm going to adjust the index of refraction, make it set it for glass. Glass is 1.6. The light is leaving the more dense medium, going to a less dense medium. Because density is going down, angle is going up, and the angle of refraction is larger than the angle of incidence. Can you see this? Watch what happens when I increase my angle of incidence. Eventually, my angle of refraction becomes 90, and total internal reflection occurs. When that occurs, that angle of incidence is renamed the critical angle. When the angle of reflection or refraction becomes 90, the angle of incidence is renamed the critical angle. We'll do it again. So we're going to set this down to water. angle of incidence, angle of refraction eventually becomes 90, the angle of incidence is 48, which means any angle 48 or larger, or angle of incidence, will cause the laser energy to get trapped. Can't leave. So 48 is my critical angle. Yeah, because water has a set index of refraction. Now, if we get a huge index of refraction, like syrup, then the critical angle is actually really small. The critical angle is only 34 degrees. At 34 degrees, then everything above this gets trapped. What's the critical angle for diamond? Oh, come on. So basically for diamond, sine theta r has to be equal to 90, which is, what's sine of 90? 1. So you write Snell's law like this. You say Ni, which is diamond, 2.4, sine theta I, which is going to be the critical angle, equals, if it's going to air, 1. Really small angle. See if you can figure it out. And this is the reason that diamonds sparkle, because that light gets trapped in there. It only has to come in at a very small point. So they grind down a surface on the top of the diamond to let all the light out. So it goes bounce, 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 out. You can also just take your phone and ask Siri what is the critical angle for diamond. She'll probably know what it is. Did you get something around 20?
24.
Yeah, 24 degrees. It's a tiny, tiny slice of angle that will allow light to get out. So most of the light that comes in on your diamond ring just bounces around inside in there for a while until it goes right out the top. So that's why diamonds sparkle, because most of the energy gets trapped in there and it comes out the top. Okay, second to last thing, probably the last thing, we'll see. Thin film refraction. I love thin film interference. And I have to turn the light on so you can see this demonstration. Now, thin film refraction is why soap bubbles, look all colory. But it's important to realize, remind ourselves, what happens when wave energy strikes a different medium. Two things happen, depending on the difference in densities. What two things happen when light energy hits a new medium? They both start with an R. When light energy strikes a new medium, some of it gets reflected and some of it gets transmitted. But yeah, sorry, they don't go with an R. Yeah. Sorry. Don't cry. Okay, so imagine a light beam comes in. Imagine a nice fat transverse wave comes in and strikes a boundary. What does it do at that boundary? Some of it gets reflected, and some of it gets transmitted. Transmitted, and then it hits the new boundary. Once again, the light hits a new boundary, so some of it gets reflected, and some of it gets transmitted. And this is why bubbles look all crazy. The reflected light overlaps with itself. In fact, it happens multiple times, because even when it gets down here, some of it gets reflected, some of it gets transmitted. It gets here, some of it gets reflected, some of it gets transmitted, and then it keeps going. And this mixing of light creates interference, where we arithmetically add the amplitudes of waves, and you get color gaps. Maybe a blue overlaps with a cyan. Maybe a red overlaps with a purple. Maybe a yellow overlaps with a blue and disappears or becomes white light. So you get these crazy color bands. If you don't like my diagram, there's another one down here. Okay. So light comes in, strikes a boundary. Some of that energy is transmitted, some of it is reflected. the light energy that got transmitted strikes a new boundary. Once again, some of it gets reflected, some of it gets transmitted. And then the interference of that transmitted light and reflected light creates these color bands. Why are the bands thicker on top than down below? Take a guess. By the way, the math of this is nasty, but we're not going to do it. You just need to know what it is. We're not going to do any math for this, because it is ridiculous. But do you have an idea why the color bands might be wider on top? It has to do with how thick the thin film is. The thin film is thinner on top, thicker down below. The thinner your film, the wider your color bands are going to be. Thin, thick, because look, the soap is thicker down here. Kind of so that's how thin film refraction works. So next time you see light bouncing off an oil slick, when there's water sitting on top of oil, that's what you're seeing. The oil is a thin film on top of the water. When you see a soap bubble, the soap is a thin film in the air. You see a compact disc, the compact disc plastic is the thin film above the reflective material. Last thing, okay. Any questions about this before I leave you with rainbows? What's a rainbow? Yeah. The word we use is dispersion. When light goes through a prism, it disperses. Long wavelength red, yellow, and orange light bend more than short wavelength purple and blue and green light. That also happens when you shoot down the neon cat. So water droplets act as a giant prism, and then the light bends in those water droplets, and it bends twice, once going in, once coming out, and you get, imagine, this is actually a really bad example. I wish the light was like here. It's coming in this way. So the light's bending, and it's bending more with a longer wavelength red light than it is with a shorter wavelength blue and purple light. What shape is a rainbow?
Circle.
Yeah, it's a circle. It's a circle. If you ever want to see an entire rainbow, this is what you got to do. You have to be in an airplane or up on a mountain, and the sun has to be behind you, and there has to be a cloud right here, and you have to be looking out the window. So if you're flying along in an airplane, keep your eyes on the instruments. Sun over there, cloud, and you'll see the rainbow over there. I've only seen a whole rainbow once. It was when I was in an airplane. But yeah, if you're up in a mountain, sometimes you can see it if the cloud is near you. Questions? Cool. Next time we have a really neat lab on Snell's law, and then on Thursday we're going to do ray diagramming, which is more like drawing.